Okay, properties of cosets. So that's 3.2, and I will talk about index. And Lagrange theorem. So, okay, so let's discuss some properties of cosets, why they are interesting. So maybe let me start with proposition number 1. And so let G be a group, and H is a subgroup of G. And then the statement is that there exists a bijection between any two cosets of G relative to H. So, I mean, it might seem weird. So there are left cosets, right cosets. What do I mean by that? So actually all of them are in bijection. Every right coset is in bijection with every left coset. And the proof is just one word. So let me explain the proof. So the proof is as follows. So the proof is that it is enough. So enough to show that any coset is in bijection with H. Why? Because being in bijection is an equivalence relation on sets of some cardinality. You cannot say all sets, but just if you subsets. Okay, so if one subset of G is in bijection with another, and second is in bijection with a third, you can take composition of bijections. So it's sufficient to show every coset is in bijection with H. So of course, if group is finite or H is finite, it will mean that actually every coset has the same number of elements. But we will deal with infinite groups in this course, and so I don't want to make unnecessary restrictions here. So for the statement, it doesn't matter whether anything here is finite or not. And so, and then let's take just some left cosets. So let G be inside G. And then we can take G times H. This is a set GH where H is inside H. And this is basically one of the left cosets. So this is a left coset. And then we have this map. So let's consider a map. So let me consider a map F from H to GH. And what this map does, just guess. It takes element and multiplies by G. And so this F is a bijection. So F is a bijection. And the reason is, of course, you can prove it's injective, you can prove it's surjective, but the simplest way is to just find F inverse. So F inverse is just a map sending element, let's say X here, to element G inverse X. And so if X was G times H, G inverse times X will be some element in the group, and these two things in composition give identity. But you can also say, okay, two elements have to go to different elements, because otherwise you can use this contraction property, cancellation property. Also, you can say, okay, if you want to get element G times something, just start with this something. And that's the proof. And so, if G is finite, if G is finite, all cosets have the same size. So for a finite group, all cosets have the same size. Actually, if just H is finite, then all cosets have the same size. Okay, so of course it has a corollary. And corollary is, this is what's called Lagrange theorem. And we discussed its Lagrange theorem. And we discussed its special case, and special case was the order of any element is divides the order of the group, and the statement is that G is finite and H is a subgroup of G. Then the order of H divides the order of G. And it just follows because, of course, order of G, so proof is just order of G equals to order of H times number of cosets. Okay, so order of G equals H times the number of cosets. Notice it doesn't matter you take left or right, but you need to be careful. You need to say which you take. Say left of left cosets. You can also say here right cosets. They still all have the same number of elements. Left cosets and right cosets decompose G into equal parts, but this decomposition can be different if you take left or right. So generally picture is something like you have your G, and then you divide it, so this is H, and then you can divide it in some way, and these are left cosets, but then you can divide it in some other way to get right cosets, and this decomposition will be generally different, except that H is both left and right coset, and their number is the same. So there is something interesting going on here, and if you have the same group, subgroup, you can wonder how left and right cosets interplay with each other. So in general, the picture can be rather complicated. Okay, so we have this interesting number, which is number of left cosets, and for a finite group, it follows it's the same as number of right cosets, and I want to discuss it in slightly more detail. So that's what's called index. Okay, so I want to discuss index, and here is a definition. So definition. So okay, let me say carefully. So cardinality of the set of left cosets GH is called index, and notation is G double dot H. So okay, number of cosets, cardinality of the set. I remind you, cardinality is this set theory idea generalizing number of elements. So if sets are infinite, we say cardinality. You can say number of elements, but you should be ready that some of them will be, countable, uncountable, and so on. So things become complicated there. So so here a few remarks. So it has some properties. So property number one. So properties. So one is that if G is finite, then it's really easy. So just cardinality is just number of elements in G divided by number of elements in H, and this is what we just saw. The fact that it's an integer number, it's remarkable, and it follows from this partitioning, bijection, and so on. Okay, so G is finite, then we have this. So another thing is that, okay, it seems that we have two cardinalities, left cosets, right cosets. So, and actually they are the same. So number of left cosets equals to number of right cosets. And of course, what I mean by that is, again, these cardinalities are the same by number. It's just, I mean, cardinality of the corresponding set. And it's obvious for a finite group because they will equal to the same number of elements in G divided by number of elements in H. And for infinite groups, we need to prove it in some other way. And notice that it might happen that group G is infinite, H is infinite, but the index is actually finite. That happens, and that's an interesting situation. So we will look at that in a second. But before, let me just prove it. And the idea is very simple. So let's take. Let me not write all details here, but the idea is as follows. So you take all left cosets, and you take all right cosets. And then, so let's just write down a bijection. And the idea is as follows. So I take coset GH, and I just send it to coset H, G inverse. So you might wonder, why do I do that G inverse? But the fact is that actually, if I just send GH to HG, it will not be at all a bijection, because it can happen that two elements are equivalent here, but not there, because these two equivalence relation being equivalent in the same left coset, in the same right coset, they are not the same. But if you know that two elements are in the same, so if two elements are equivalent kind of from the left side, and it means that x, and y, and it means x inverse y is inside H, then you can take x inverse and y inverse, and you will get that x inverse is equal to y inverse if you think about right cosets. And the reason is because if you now do, so here we do the same thing, but just we take now x inverse, y inverse, inverse is inside H, and of course this is the same thing. So you need to exchange element with its inverse, and then left cosets and right cosets will go to each other. So that's the proof why index doesn't depend on whether I put right or left here. I can say here left, and I get the same number. So, and another property which is really important is that imagine I have G, subgroup H1, subgroup H2. So as we discussed before, I guess a subgroup of a subgroup is again a subgroup, because just check all axioms, it's really easy to see. And then of course we have now three indices. There is this index, GH1, and there is this index, H1, H2. Finally, there is this big index, GH2. And the statement is that actually G then GH2 equals GH1 times H1, H2. So what does that mean at all? So, I mean, there are various ways to think about it. So if all numbers are finite, that's equality of finite integers. If one of them is infinite, you understand it as you might expect. If it is infinite, you expect one of these two things is infinite. Otherwise, you can say if these two are finite, this is finite. And then basically this is what it means. Okay, so this is true, but let me not prove it for infinite groups. I will assume just G is finite. So proof, and I assume G is finite, and you can think a little bit about what happens for infinite groups, and then of course you just show that the order of G divided by the order of H2 is just equal to the order of G divided by the order of H1 times H1 divided by H2. So we will discuss infinite case during the class. Okay, so maybe let me finish with an example. So for instance, you can take as G equal to Z and H equal to 2Z. So 2Z is usual notation for even integers. You just take all numbers which are, -2, 0, 2, and everything before and after, and then you can look at cosets, and basically there are two cosets, and there are two elements there. So one is a subgroup, and these are just even numbers, and the other coset is of course just odd numbers. So numbers equivalent to 1 with respect to this subgroup. Okay, so again, all this business with left and right cosets, it's basically this distinction doesn't exist if group is abelian. Every left coset is at the same time the right coset. But in general, the things are different. So now let me discuss a special kind of subgroups for which left cosets and right cosets coincide. They are called normal subgroups, and they are very important.